Very good morning to all of you. Now, the content that was covered in previous session was regarding the SCR, turn off characteristics of an SCR. That was towards the end of the previous session. That the reason why SCR is not turning off is because of the location of gate. The gate is located very far away from majority of the cathode portion. So that makes the gate ineffective for a very large portion of the cathode. Therefore, even if we apply a negative gate pulse, the SCR is not going to be affected. So this can be recollected from or understood from the two transistor analogy. If we apply a negative base for one transistor, let's say the NPN transistor T2, now that transistor T2 will not be turned off because the base is again being supplied by the collector current of the PNP transistor. So that positive chain reaction mechanism will keep going on, even if you apply a very small negative gate pulse. So that is the reason why the gate is not having control over the SCR after it is turned on. Of course, there were two important currents. One was the holding current, another one was the latching current. I think we did in earlier sessions. Holding current is mainly important for turn off process. If you want to turn off the SCR, anode current should be brought down below the holding current and sufficient reverse voltage must be applied so that the SCR regains its reverse blocking capability. That is the turn off mechanism for you. And turn on process, latching current is going to be important. We need to apply a gate pulse till that latching current, till the anode current reaches that latching current value, or till that positive feedback mechanism commences. That is when the SCR is going to begin to conduct and carry some anode current. That is regarding the anode, latching current value or latching current definition. Generally, latching current is more than holding current. Always, not generally. Always, latching current will be more than the holding current value. Those are some other some points which we had discussed regarding SCR. Today's session will be on power MOS. Sharing my screen, and I'll start today's session, which will be on power MOSFETs. I'm sure you can see my PPT. Now, today's session, we will discuss the structure of a power MOSFET and its operating principle. Now, the structure of a power MOSFET is going to be a vertically oriented structure. So we have the orientation is going to be from top to bottom, source to drain, or you can look at the other way around as well, drain to source. But generally, we start from the source to drain because of some reason. That reason is okay, fine. Now the structure of a power MOSFET is going to be a vertically oriented structure. Vertical orientation refers to the fact that we need to move from top to bottom, whereas in other power devices, even the lateral structure is going to be fair enough. So this is one important point that you need to understand. I will denote that as well. I will write somewhere inside the slide so that you can refer to that at a later time. So vertically oriented structure. This is one point which you need to remember. The reason why this is important is due to the fact that you will have metallization on top and followed by you will have metallization. This is the metal portion. This portion serves as the source metallization, whereas you will have the metallization for gate as well, gate metallization. Of course, it's a vertical oriented structure, but when you look at the device, they will be parallel, meaning source and they may look that they are interfaced here. It is not like that. They will be side by side. Source and gate will be located side by side, and each will have its own oxide layer. One is called as field oxide, another one is called as gate oxide. So the oxide layer beneath the gate terminal, that is referred to as gate oxide layer, followed by the classical semiconductor layers. You have 4 layers. You will have the N plus. Any doubt? Should I wait? Is somebody having a question? People, okay. Person is muted. Fine. So you will have a N plus substrate, obviously the heavily doped layer, and then the N minus drift region. Again, the obvious fact is that the N- drift layer, thickness of the N- drift layer will determine the voltage blocking capability. This is also called as N- drift layer. Please remember that N- drift region I have indicated here. So this determines the voltage blocking capability, followed by the P-type body layer. Now the P-type body layer, this is the I hope you understand what is called as the body layer. You will have contact, that is the user will have contact, and then comes the heavily doped N plus layer, which serves as the source. Now, if you look into the structure, the N plus body layer and the, sorry, N plus layer and the P-type body layer will be short circuited. There is a short here. Now that short is referred to as, there is a short here. This short is referred to as body source short, which means practically when you get that MOSFET, you can use the body layer as a source. The advantage of that is current is going to sink through the source. Therefore, sink means it will flow from the drain to the source. So the source will act as that sink. So you can sink it, meaning you can have a heat sink attached to that source, and the drain current will cause a heat, and that heat will be easily dissipated. That is the meaning of, that is the purpose of this body source short. Now, the importance of this vertical oriented configuration is when we look from top to bottom, we have metal here. This is metal. Of course, I am referring to the source metallization. Gate metallization can also be checked. This I will refer to as gate metallization or gate contact. Metal, we have metal here first, and then comes the oxide layer. So metal layer is followed by the oxide layer, metal oxide, and then you have the semiconductor layer, followed by the semiconductor layer. Now, if you look into the operating principle, the device is going to operate based on field effect. Therefore, we call this device as, sorry, it should be field effect. Field effect. Now, if you just join or look at the first terms, M, O, S, F, E, and of course it is similar to a transistor. Therefore, it is termed as metal oxide semiconductor, and it works on field effect. So it is metal oxide semiconductor field effect transistor. That is the expansion of MOSFET, metal oxide. So you have first is metal, M for metal, O for oxide, S for semiconductor, and it operates on the principle of field effect. Therefore, FET stands for field effect transistor. So you get this MOSFET. Now this structure, vertically oriented structure, if you look at that, you will get this understanding. That is why the vertical oriented structure is important, something what I mentioned in my opening remark. Now, whatever structure we are seeing is actually an N-channel MOSFET, N-channel enhancement mode MOSFET. You do have P-channel enhancement and N-channels, they are preferred. Now, the symbol of this MOSFET is, see, the gate is actually, if you look at this gate metallization, gate is actually insulated from the gate oxide. So it doesn't get insulated by the gate oxide. So it doesn't have a direct contact. Therefore, you will have to include that insulation level somewhere in the symbol. So we draw the symbol like this. Firstly, we put a gate, and then with the metallization, you don't have any direct contact. There is only insulation. Therefore, the terminals have to be insulated. And then you have this source. This is source terminal. This is drain terminal. Obviously, this one is the gate. So this is the symbol of an N-channel MOSFET. Please try to understand this in case you are coming across this symbol for the first time. If you have come across that in semiconductor devices, it is fine. And the arrow mark should be pointing inwards for the N channel. For the P channel, it will definitely be pointing outwards. This is one symbol. And when you look at the operating principle, the first look, I'll pass on to the next slide. The first look will tell that you don't have any direct path for current. See, you have only the drain current. ID is actually the drain current that should flow through the device. This is the drain current. ID. This is required to flow from the drain to the source. The drain current starts from the drain and then it has to flow into the semiconductor material and then it has to flow to the source terminal. This is one path, obviously drain, and this is the source. So this is the other path. I hope here you don't have any lag or it's somewhat continuous. That's what I believe is happening. So that is the path for drain current. But if you look into the structure, see here you have a p-type body layer and then you have a n plus layer. So this forms a junction, a p-n junction over here. Again, you have the same p-n junction over here on either side. You will have p-n junction, p-type body and n plus source. P-type body and n plus source forms a junction. But then junction has to be forward biased suitably. Now, irrespective of whatever polarity you apply to the source, suppose you apply minus to the source and then plus to the drain, still this will be reverse biased. You apply plus to the n plus region, still this is going to be reverse biased. Therefore, you won't have any direct path for the current to flow at once. That is the inference. You will not have no actual direct path for current flow. I will write ID for drain current ID. This is actually the first impression. Later on something happens. That is the operating principle. But still it conducts. For conduction to happen, there has to be a channel which must be established. For ID, for drain current to flow, I said N channel, no. So I will write an N channel must be established. Must be formed or established. Where should it be formed? Between the p-type body and N plus interface, source interface. That is, I am referring to this region. Okay. So here a channel, that to an N channel, must be established. Let us see how the N channel gets established. Only when this channel gets established here and here also. This is again the p-type body layer. This is again the p-type body layer N plus interface. This is also the p-type N plus body layer interface. So channels must be established between the p-type body and the N plus layer. Everything is interconnected. Inside the structure, they are interconnected. So this is where field effect is going to be helpful. Let us try to understand that field effect principle. Before we understand that, internally, there is a parasitic BJT. I have marked here, which is formed by the N minus p-type body and N plus source. So you have this parasitic NPN transistor, and you have an integral body diode as well, p-type body and the N minus N plus perfect diode. See, the power diode had N plus structure, N minus structure, and p-type body. So again, p-type N minus N plus. So this forms the body diode. Therefore, there are ways to represent this integral body diode in the symbol itself. That is one way. Another important point is the parasitic BJT should not be turned on. When this diode is going to be on, then there will be a current that is applied to the base, this parasitic BJT, and it will turn on. It may cause some issue. So this parasitic BJT should not be turned on. The applied field effect that takes care and makes sure that the parasitic BJT is always off. But this integral body diode, you can't avoid it. The effect of this body diode alone can be neglected, or rather reduced, not neglected. It can be brought down, reduced by doing some structural modifications. Nevertheless, to indicate this body diode, in the symbol, sometimes if the effect of that body diode is more pronounced, then people actually refer to that body diode and indicate it clearly in the symbol itself, like this. There will be the drain, there is the source. If you look at the structure, from the source to the drain, there is an antibody diode. So this is another way of representing the MOSFET when the antibody diode and its effect is going to be more pronounced. So, antibody diode. It's called as antibody because it is opposite to the current flow. Drain current flows from drain to source, whereas this diode can conduct only from source to drain. So that is why we call this as antibody diode. It is opposite to the drain current. That is also indicated in the structure. You can look at here. The ID flows from drain to source, whereas the diode is opposite to the drain current. So compare this ID, flow of ID from bottom to top, and the fictitious current that would flow through the integral body. So these are few points that you need to understand with regards to the structure of the power MOSFET. Now let us take up the operating principle of the power MOSFET. It works on field effect principle, very, very simple. I'll have to take another mode, so I will do that. So now it should be fine. Okay, so 20 seconds, no. Iteration of MOSFET. Now, if you want to understand the operating principle of a power MOSFET, you need to keep in mind that power MOSFET needs an N channel. We are discussing N channel, so it needs an N channel. N channel must be formed. Once the channel is formed, operation is over. That's all. That is the principle. How the channel is formed, let us try to understand. That's what we will be discussing now. Now, the first and foremost time when a small gate voltage VGG, I have indicated that as VGG1. This is a small magnitude of gate voltage. So the first time a small gate voltage is applied, there will be the applied voltage will actually repel the holes, and some sort of a depletion layer is going to be created. So these are ionized acceptor atoms. I will write them somewhere here, and a small depletion layer is going to be created. This is the depletion layer. Depletion layer. And these are ionized acceptor. So that is the first step which happens. I will write that first step as well. Small VGG creates thin depletion layer. I hope you understand what a depletion layer means. It means that there are no mobile charge carriers, which means the applied positive voltage will repel the holes away from this layer, away from this N plus P type interface. So that is why a depletion layer is created, creates a thin depletion layer because of repelling because the I will write because the holes are repelled away from the portion just beneath the gate oxide layer. I'll write it that way. From the portion just beneath the gate oxide layer. Now, which is the gate oxide layer? I hope you can understand this. This is the gate oxide layer. So this is the gate terminal. That is why it is VGG. So this is gate metallization. This is source metallization. Drain I haven't indicated, that I will do. Anyway, finally I will draw the drain, but for clarity, the drain metallization is going to be somewhere here. Black, so I have used black. So this is where the drain terminal will be. Oh. So this is drain contact. So all the three terminals are available. Now, just beneath the gate layer, I am referring to this point. Just beneath the gate oxide, the holes are going to be repelled inside. Repelled away. Somewhere here, repelled here. Therefore, there will be free. They are free charge carriers, but they are immobile. Therefore, they are termed as ionized acceptor charge carriers. This is the first step that happens. Second thing is, if you further increase VGG, so that image I will use here. Yes. So next step is, I have deliberately put this as VGG1. Now what I will do is, instead of VGG1, for our understanding, I will write VGG2. Now you need to understand that VGG2 is higher than VGG1. That is, I am further increasing the gate voltage. When I further increase the gate voltage, this is where the capacitance effect creeps in. Now you have gate metallization, you have oxide, and you have semiconductor. So this behaves like a capacitor. In fact, it is called as mass capacitor. Therefore, when you apply a when you apply a positive potential to the gate, negative potential will automatically be induced, right? And the amount of negative charge carriers that are induced, that will be same in magnitude due to capacitance effect. This is one way, easier way of understanding. Another way is, because the applied potential has increased, the width of the depletion layer will increase. Earlier, if it was thinner, now it will become thicker. Not only that, because of the applied voltage, it will draw electrons. It will, let's say, attract free electrons from the N plus layer. So the free electrons, these things are free electrons. Free electrons, whereas this is the depletion layer boundary. Now the free electrons, they are going to be attracted towards the point beneath the gate oxide layer. What is the source of this electrons? N plus layer, because N plus layer is having more number of charge carriers, majority charge carriers in the N plus layer, they are electrons. So the sequence of events is, when VGG2 is applied, VGG2 is more than VGG1 is applied, width of the depletion layer increases, the applied positive VGG attracts electrons. This is actually field effect. All right. It attracts electrons and simultaneously it will repel holes as well. That is why the width of the depletion region increases. That is why this happens. Okay. Now, when the electrons are going to be attracted, the source must be written. Immediate source of electrons, or immediate source of electrons. They are actually free electrons because they can move. Therefore, they are free electrons. Immediate source of free electrons. This is the N plus layer. Okay, fine. So I will move to the previous page and then let us see the difference between the previous page and the present page, which means between VGG1 and VGG2. Now, first, when VGG1 is applied, small gate voltage. When a small gate voltage is applied, just a thin depletion layer would be formed. This is just a thin layer of depletion layer. Thin depletion layer. Undo. Okay, fine. So there won't be any free electrons. Okay, whereas you don't have any free electrons here when it is VGG1. Now I'll move to the next page. Whereas when we slightly increase the gate voltage, depletion layer grows in thickness. That is okay. But because of the applied field, there will be free electrons which are attracted towards this gate oxide layer, beneath the gate oxide layer, just beneath that. They are getting attracted. From where do they come? They come from this N plus layer. Right? So due to the applied field effect, free electrons will be attracted. Of course, I will write the location as well. Attracts electrons. The free electrons will move closer to the layer which is